Have you ever wondered what that invisible force is that shapes our entire universe? The one that keeps our feet planted firmly on the ground and, at the same time, orchestrates the grand cosmic dance of planets, stars, and entire galaxies? Well, today, we're going to dive into one of the most fundamental questions in all of science.
It seems like such a simple question, right? I mean, we feel its effects every single second of every single day. But if you really stop and think about it, what is it? How would you even begin to describe it?
And hey, if you are thinking something along these lines, you are in very good company. These are totally intuitive ways to think about it. It's that pull, right? That attraction, the thing that just keeps us all here. But to really get it, we've got to go a little deeper.
Okay, so let's start with the basics. What are the fundamental rules of this pull that we all feel every day?
So this definition gives us two really crucial pieces of the puzzle. First, gravity is generated by mass. Anything that has mass. That means you, me, this planet, even a single atom has its own gravity. And second, it's always attractive. It only ever pulls, it never ever pushes.
And this brings us to a super important point that trips a lot of people up: the difference between mass and weight. Your mass is basically the amount of stuff you're made of, and that number is constant. It never changes. Doesn't matter where you go in the universe. Your weight, on the other hand, that's just the measure of gravity's pull on that mass. And believe me, that can change. A lot.
And check this out. This chart just illustrates the point perfectly. Let's say you're a 100-pound person here on Earth. On the Moon, which has way less mass, you'd feel incredibly light, weighing only 17 pounds. But then, if you could stand on the gas giant Jupiter with its absolutely enormous mass, you'd be crushed by a weight of 253 pounds. In all three places, your mass, the amount of you, is exactly the same. But your weight is completely different.
So, for centuries, people knew that things fell. Duh. But they didn't really have a mathematical rulebook to explain the why or the how. That all changed back in the 17th century thanks to one guy, Sir Isaac Newton.
Now, Newton didn't just pull this out of thin air. He was, as he said, standing on the shoulders of giants. You had Copernicus, who put the sun at the center of everything, then Kepler, who figured out the weird oval-shaped paths of the planets, and Galileo, who showed that all objects fall at the same rate. Newton was the one who saw all these puzzle pieces and put them together.
You know, the story about the apple is famous for a reason. It perfectly captures his incredible insight. He saw that apple fall and he realized that the force at work right here on Earth
Was the exact same force that reached all the way out into the cosmos and held the moon in its orbit around the Earth. It wasn't two different sets of rules. It was one. It was universal. I mean, what a revolutionary idea, right? It connected the heavens and the Earth under a single beautiful law.
And Newton's law basically says the force of gravity boils down to two things, mass and distance. The more mass something has, the stronger its gravitational pull. And the farther away you get, the weaker the pull gets, and it drops off fast. If you double the distance, the force of gravity drops to just 1/4 of what it was.
And man, did this law work. It was a triumph. It could predict the orbits of planets with stunning accuracy. It explained why the oceans have tides. It's the moon's gravitational pull. His law was so powerful that in 1846, astronomers noticed the planet Uranus was wobbling a little bit in its orbit. And using Newton's math, they predicted the exact location of a planet nobody had ever seen before. And when they pointed their telescopes there, boom, there was Neptune.
For over 200 years, Newton's law was the final word. It seemed absolutely perfect. But as our ability to measure the universe got better and better, a tiny little crack started to show. And it would take another genius to come along and completely flip our understanding of gravity on its head.
So, what was this nagging little problem that had astronomers scratching their heads? Well, it was a strange little anomaly happening right here in our own solar system. The culprit was Mercury. The little planet closest to the sun wasn't behaving exactly like Newton's laws said it should. Its orbit was shifting by this tiny, tiny amount, just 43 arcseconds per century. I mean, that is an unbelievably small slice of the sky. But it was a real discrepancy, and for physicists, an error you can't explain is a very big deal. Newton's gravity just couldn't account for it. Then, in 1915, Albert Einstein comes along with his theory of general relativity and offers a completely radical new idea. He said, what if gravity isn't a force at all? Instead, he imagined that space and time are woven together into a single, flexible fabric, spacetime. And what massive objects like the sun do is they literally warp or curve this fabric. So the Earth isn't being pulled by the sun, it's just following the straightest possible path through the curved space around it. That curve is what we feel as gravity.
Let's just put these two ideas side by side because they're fundamentally different.
For Newton, gravity is a force, kind of like an invisible rope connecting two objects. For Einstein, gravity is geometry. It's the actual shape of the universe being bent by mass and energy. And get this, not only did Einstein's new theory perfectly explain Mercury's weird orbit, it made some other predictions that were truly mind-bending.
Yeah, Einstein's new vision of gravity wasn't just some minor correction. It opened up a whole new cosmos, one filled with some of the most bizarre and extreme phenomena you can possibly imagine.
His theory predicted some crazy stuff, like the path of starlight should literally bend as it passes by a massive object, and that time itself should run slower in stronger gravity, a thing called time dilation. We actually have to account for this in our GPS satellites every single day or they'd be useless. And it predicted the existence of black holes, places where space-time is so warped that not even light can get out, and ripples in the fabric of space-time itself, which he called gravitational waves.
And then, in 2015, exactly 100 years after Einstein first proposed this theory, scientists at the LIGO Observatory directly detected gravitational waves for the very first time. They captured the ripples in space-time sent out by two black holes colliding over 1 billion light-years away. It was one of the most incredible confirmations in the entire history of science. But even with the stunning triumph of Einstein's theory, the story of gravity is far from over. In fact, we might be on the verge of another massive revolution, because right now, gravity is at the center of the biggest mystery in all of modern physics.
So here's the problem. We have two amazing theories that describe our universe. General relativity is our theory for the really big stuff, planets, stars, galaxies. And quantum mechanics is our theory for the really small stuff, atoms and particles. Both work perfectly in their own domains. The issue, they're totally incompatible. They don't speak the same language. And this clash becomes a huge problem when we try to describe gravity on the tiny quantum scale.
And if you want to see just how much we still don't know, just look at this chart. All the normal matter, everything that makes up you, me, the Earth, the stars, all the galaxies we can see, that's only about 5% of the universe. The rest is made up of dark matter and dark energy, two things we know are there only because we can see their gravitational effects. We have no idea what they are, and our current theories can't fully explain them.
So that leaves us with this final, profound question. We've come so far, from Newton's apple to Einstein's warped space-time. But with these huge mysteries like dark matter and quantum gravity still unsolved, you have to wonder, is our quest to understand this fundamental force finally wrapping up? Or is the most exciting chapter just getting started?